Hello, and welcome to Physics for Play. In this video, we're going to look at the different types of physics you get as you change the damping from small to large. Let's get started. Well, today we're going to consider some special cases for the simple harmonic oscillator that is damped. We're going to look at the cases where you have just a little bit of damping, the case where you have a lot of damping, so the frictional force is very large, and we're also going to look at the case where it's critically damped, and I'll define what that is momentarily. So to begin, let's start with that underdamped case. So I am just going to go back to my solution. I'm going to copy this, and I'm going to paste that in here. And we're gonna start with the underdamped case. And for this, I'll choose b equals 0.5. And I actually want to get a plot of this. So I'm going to go up and I'm going to steal the plot of x of t. And I'm going to paste that in here. So the beautiful thing about working in code rather than pen and paper is that once you've solved something once, you just copy and paste and you can solve it in a whole bunch of different ways. So we're going to look at the underdamped case here. So this is where I have damping that's a relatively small number. And I'm actually going to put in a little bit more information here. So I'm going to scroll up. And as you will recall from an earlier video, we had written down this solution. And if you'd gone through the exercise, you can show that if you make a guess, you can write down your solution in this way. And we had a few different constants that we had thrown up here, which I'm going to copy down here for convenience. So in addition to the parameters from the initial differential equation, you got your spring stiffness, your mass, your damping constant. We defined these other constants, the first of which was the natural frequency. The natural frequency is the angular frequency at which the system would oscillate at if there were no damping. I defined this new damping constant, which was basically just a rescaling of the original damping constant. And we defined this angular frequency for the new oscillator. Now, the astute among you will note that there's a square root here, and there's two terms, and one of them has a minus sign. So what happens if omega naught squared is bigger than gamma squared over 4? Well, if that's the case, so this is the case where gamma is pretty small, which in this case I've chosen a gamma that's pretty small. If that's the case, then this omega, my angular frequency, will be a real number. It'll spit out a frequency as you would have in a sine and cosine function, which means it'll oscillate up and down. And that's exactly what you see. This is the underdamped case, where the gamma squared over 4, the damping, is smaller than the restoring force. Or I should say the natural frequency, which is dependent on the restoring force. So if omega naught squared is bigger than gamma squared over 4, your frequency is real, everything's hunky-dory, you get a nice oscillatory function that just decays over time. Now, what happens if instead of having just a little bit of damping, we have a whole lot of damping? So we're going to try that in this case. So you can see, since I outputted it, since I removed the semicolon, we could see that here our angular frequency was a little less than 1, about 0.96 or 0.97. Now I'm going to change this up. I'm going to make my damping constant bigger. I am going to choose what would be a good. Let's just overdo it. We're going to make the damping constant. I'm going to toss that up to 10. Now, when I look at the angular frequency equation, I'm going to get an omega naught squared, Well, omega naught squared is k over m. K is 1, m is 1, so omega naught squared will be 1. And I'm subtracting gamma squared over 4. But gamma is b over m. B over m is going to be 10. 10 squared is 100. So this is going to be a big negative number, which when you combine it with a 1 is going to give you still a negative number. The square root of a negative number gets you an imaginary number. So what happens when you have an imaginary frequency? Well, an imaginary frequency is no frequency at all. So when I plug this in, you can see it just decays. There is no oscillatory functions. If I look up in here into the actual analytic form, there's no sines and cosines showing up to make life easy. It just decays. If I look at the value of omega, you see I have a purely imaginary number. I've got a 2 square root 6. If I want to turn that into a fraction, or a decimal rather, I can just input I'll make this a decimal number, and then Mathematica won't assume that I want to track all of the real numbers to infinite precision, and it'll spit out a complex number that has 0 for the real component and 4.89898 for the imaginary component. That's purely imaginative. So here we don't get any oscillations at all. The harmonic oscillator just decays. This is a case where if you imagine your spring, you put it in molasses or something really slick, really thick rather, you displace it and it just kind of slowly goes back to equilibrium because the damping force is so much bigger than the restoring force of the spring. The spring is not going to overshoot and cause that oscillation. But there's an interesting middle case here. So what happens if the angular frequency is exactly equal to 0? So what happens if the omega naught squared and the gamma squared over 4 exactly cancel out? Well, we can test that. That is the case of critical damping. So here, k is 1, m is 1, therefore square root k over m is going to be 1, omega naught is going to be 1, which means omega naught squared is going to be 1. So if I want omega to be identically 0, I need gamma squared over 4 to be identically 1, which means I need gamma to be 2. So I need b to be 2. So we're going to run this, and we will see, just run this cell. Here we're outputting the angular frequency. We see that is identically 0. And we've got an interesting function here. We've got both an exponential decay, but also this linear term that grows linearly with time t. The exponential decay will win out at large times, but you can see that is going to decay relatively quickly over time, and we can see that in the displacement function. I should note, just because we did it for the earlier examples here, if you want to see how the energy behaves, we can certainly look at that as well, because we looked at that when we were looking at the different plots. So I'm just going to go ahead and steal my energy plot from before. All we have to do is plug that into the different cases. I'll just do it for the critically damped case so you can see what it looks like. We'll run this one more time. And you can see, that was an error in the last video. I never corrected that. That should be energy. And that should be in joules. And we can see how our energy changes over time. You can see the total energy is just the sum of the two. And the kinetic energy, potential energy, and total energy all just decay at long time until the oscillator no longer has any energy and is just restored to its equilibrium position. That is it for now. Join us next time where we'll continue discussing the damped oscillator, but we'll be looking at it through our first case of a nonlinear equation, where we'll consider a different type of damping force that doesn't just go, that's not just proportional to the velocity. Like the video if you liked it, and if you'd like to see more of these, please click subscribe.